Welcome to the second half of our lecture on atmospheric stability. This is from your book, Chapter 5 on water in the atmosphere. We're going to start off with a quick recap of what we went over in the last lecture. First, we looked at the governing controls of vertical movement in the atmosphere, those three major factors that move air up or down in the atmosphere. First, there was the opposing forces of buoyancy and gravity. Buoyancy force wants to move the parcel up, push it up in the air. Gravity force wants to pull it down towards the surface. There was also air density. Warm air parcels are less dense and rise. Cold air parcels are more dense and want to sink. And then there's just the overarching effect of air pressure in general, that as you go up in altitude, your air pressure is going to decrease because there's less air above you. And as you go down in altitude, you move towards the surface, air pressure is going to increase because there's more air above you. We also looked at adiabatic temperature differences. Changes in temperature due to adiabatic processes do not involve any actual exchange of heat energy. Changes in the temperature, when we're talking about an adiabatic process, are due only to the change in volume of the air parcel, to where when it expands it cools, and to when it contracts it warms. And this expansion and contraction is due to changes in air pressure. And then finally we looked at lapse rates. Lapse rates is the change in temperature over distance. So as we go up in the atmosphere, for every 1,000 meters we go up, our temperature of our air parcel is going to decrease at a certain rate, and as we go down, it's going to increase at a certain rate. This time, we're going to look at stability scenarios. You've heard the forecasters say our air is stable, or it's unstable, or maybe it's conditionally unstable. We're going to find out what each of those means. We're going to look at what happens when air flows over mountains and something called the rain shadow effect. Then we are going to look at four major lifting mechanisms, processes that shove air up into the atmosphere, sometimes whether it wants to go on its own or not. And then we will end up by looking at clouds and precipitation.
So what the heck does atmospheric stability even mean, really? Well, in simplest terms, atmospheric stability is just how air behaves in the atmosphere. We've got two basic kinds of stability, stable and unstable, and then a third one that's a little more exotic that we won't go into too much, but it's good to know, which is conditional instability. In a stable atmosphere, the air resists rising or moving. This is because it's either the same temperature as the air around it, the surrounding air, or it's cooler and it's denser, and then it wants to sink. Either way, it will not rise or move unless it is forced to do so by some mechanical outside force. Typically, stable air leads to clear, crystal blue skies. We'll see why in just a second. Unstable air, this is basically what we have going on in the atmosphere most of the time. This is when the air in the air parcel is warmer than the air around it, and it wants to rise. And as it rises, it cools, and this can lead to clouds and storms and turbulence. So a lot of times when we have unstable weather, it will eventually lead to some bad weather. So let's take a look at unstable first. Notice the storm cloud. Again, pretty much what I just said. Unstable air parcels rise on their own. They don't need to be pushed up. They want to do it on their own because they are warmer and less dense than the surrounding air. As they do rise, if they have any moisture in it, in that air parcel, it's going to condense. Once it hits the lifting condensation level, it's going to form clouds, and it could very easily turn into some bad weather, some storms, a lot of gray skies, and maybe even some thunder and lightning. This is just repeating what I already said. Unstable conditions often lead to bad weather. The unstable air parcels are warmer and less dense than the surrounding air and rise on their own. All by their little own selves, they don't need any encouragement. Now, a stable atmosphere. Notice the picture here. This is a nice sunny day, bright skies. They're pretty clear. There's a couple of clouds. This happens a lot when we see these nice clear skies. Basically, we're probably looking at stable conditions, a stable atmosphere. This is where those stable air parcels are cooler and denser than the surrounding air, and they will not go up any further in the atmosphere that they are already sitting unless something forcibly causes them to do so. And this slide is just basically looking at the relationship between the dry adiabatic rate, the moist adiabatic rate, and the environmental lapse rate. Depending on how those relate to each other, it can produce 3 different atmospheric conditions. We can have unstable, conditionally unstable, and stable. I am not going to go through all of these. You do not need to know all of these. If you are really wanting to look at these different relationships, you can either stop the video or go check out the PDF I have up on Moodle. Instead, we are going to look at this graphic from your textbook. This is showing you the 3 different stability scenarios, and we're going to go through each one and figure out exactly what is going on. Let's kind of take a closer look first to really kind of orient ourselves. So we have altitude on the y-axis. We are going up. Land surface is at the bottom. On the left-hand side of your arrows in the center here, we are going to, these first 2, unstable and stable, we are going to just use the dry adiabatic rate. Let us assume that this is an unsaturated air parcel. So on to the left of the blue arrow is the ambient air temperature. This is the temperature outside the air parcel. This is basically, you would use your environmental lapse rate here. And then to the right of the arrow for each of these is your air parcel, these little balloons of air, and each one is marked with the temperature. So let's take a look at each one of these in turn and kind of see how they vary. First, we'll look at unstable. In an unstable atmosphere, the air parcel is warmer than the ambient air around it. So let's see how this plays out looking at this graph and going up in altitude. Both the outside environmental air and the air inside the air parcel start at the land surface at 30 degrees Celsius. Look how those temperatures compare as they go up. At 1,000 meters, the air parcel is warmer than the environmental air. At 2,000 meters, the air parcel is still warmer than the environmental air. Same thing at 3. It has stayed warmer than the outside air, the ambient air, this whole way up. It is unstable. It is warmer than the surrounding air, and it wants to rise. The air is less dense. It wants to rise and expand. Now let's go to the stable scenario. Let's look at the temperatures here. We're starting again at 30 degrees Celsius for both the air parcel and the surrounding air. But as we go up, let's see how those temperatures compare. At 1,000 meters, the air parcel is 20 degrees Celsius, but the ambient air is 25. So the air parcel is cooler. And we see the same pattern as we go up. At each 1,000 meters difference going up in altitude, that air parcel is consistently cooler than the surrounding outside air. So it's going to be colder, it's going to be denser, and it is going to want to sink, and it's not going to go up of its own accord unless somebody gives it a good swift kick. This is a stable atmosphere. Now our third one. This is conditionally unstable. This is not going to be on your exam, but it's good to be aware of. This is a little more complicated. Let's take a look. So with conditionally unstable, circumstances. What we're dealing with is an air parcel that is stable. It is colder than the surrounding air, or the same temperature as the surrounding air, at the ground surface and at a certain level until it hits in altitude the lifting condensation level, the point at which that parcel becomes saturated. Now bear in mind, below the lifting condensation level, it's stable. It's colder than the environmental air. Something's going to have to give that thing a push to get it moving upward in the first place. Once it starts moving and it does hit its dew point temperature, now let's see what's happening. So we start at the lifting condensation level and wait a minute. Now if you compare the environmental temperature to the air parcel, it's actually warmer compared to the outside environment. And at this point, it can start building a lot of clouds. So this is conditional instability because it's stable below the lifting condensation level and something had to give it a push to get it moving upward. And it's unstable after reaching saturation. So, fun fact, this is going to be something similar to this, not the conditionally unstable one, but the other two are going to be on your exam. So, let's do some practicing here. Let's look at this diagram here and ask yourself, is it stable or unstable? What is going on with the air parcel temperature with altitude as compared to the external environmental air with altitude? It is stable. Why is it stable? Because the air parcel is cooler at every altitude than the surrounding air. So it's going to want to sink. It's not going to want to rise at all on its own. If it happened to be the same temperature as the ambient air, it probably wouldn't go anywhere. It would just sit there. But generally, it's cooler than the surrounding air and it wants to sink. How about this scenario? Stable or unstable? Give it a look. This one is unstable. Why? Because at every different change in altitude, every 1,000 meters, if you look, the air parcel temperature is warmer than the ambient air. And that means that it is going to be warmer than the surrounding air. It is going to be denser than the surrounding air, and it is going to want to rise. And once it rises, there's a really good chance it could cause some bad weather or some storms, or at least a whole bunch of clouds. So that was pretty much it for basic stability scenarios. Now we're going to move on to an interesting phenomenon that occurs when wind hits into a mountain range and is forced upward. We call that orographic lifting. We will talk about that more when we get to actual lifting mechanisms. Right here, what we're interested in is what happens to the temperature of the air and the moisture in that air when it goes over a mountain range. Two terms here you need to know, and moving forward, this will serve you really well. Winds are typically named by the direction they come from. So like we talk about the prevailing winds in the mid-latitudes come from the west, we call those the westerlies. Around the equator, those come from the east, we call them the trade winds or the easterly trade winds. Well, here are two other terms. These are two terms that were actually, their origin is sailing. It's a nautical origin, windward and leeward. So these were words that are used by sailors and have been for goodness only knows how long. They are talking about, they want to orient themselves as they were going along a coast. They were sailing up a coast. The side of the ship that the wind was hitting from the ocean was called the windward side. And then the leeward side, lee means like shelter. So the side of the ship that was close to the land was the leeward side. So they would use these terms when they were talking about winds too. So if wind is coming into a mountain range, that moving air meets the windward side of the mountain range, the side that's facing the incoming wind, and it gets forced upward. It's coming straight at the mountain. It can't go down. Might go a little bit to the side, but mostly it's going to get shoved up. And when it gets forced upward, it cools adiabatically, causes some clouds to form. The clouds rain out, and then it flows back down the leeward side of the mountain, the protected side of the mountain, and it warms adiabatically. So let's take a little closer look at how that works. Okay, here we have a mountain range. I'm going to say, because I'm from California, that it's the coast mountains along the coastline of California. So that would be the Pacific Ocean off to the west there. We're in the mid-latitudes, so our prevailing winds are coming from the west. They are coming in on the windward side of the mountain. The leeward side is the protected side of the mountain that faces in towards the center of the continent. So here are prevailing winds. They are coming in from the west. As they are flowing across the ocean, they are picking up moisture that's being evaporated off the ocean. So that wind flows in, it hits the mountain because it's got nowhere else to go and it's shoved up. As it gets shoved up in altitude, we are having our air pressure lessen, therefore that air is expanding and cooling because the pressure is being released. As it cools, it will hit the dew point temperature, whatever that might be, and it'll start to cause clouds. If you have ever visited someplace with a mountain range around it, or you're from the mountains, you know that very often you will see a line of clouds like paralleling the mountains. This is why. So then we've got our mountains over here with water forming over them, with clouds rather. And those clouds want to rain out. They will primarily rain out most of their moisture on the windward side of the mountain. Once they have rained almost all the moisture they have, they might continue on and have a little moisture, but they're going to then descend down the other side of the mountain. As they do that, the air pressure is going to increase. Whatever moisture was in them is probably going to be squeezed out because that increasing air pressure is going to compress that air parcel. As it compresses, it's going to heat it up. And then it's quite a bit drier. There's less moisture in it to begin with because it all rained out on the windward side. Now, if we look at what's going on adiabatically, just what's happening with the pressure differences, we have a fairly warm air parcel coming in off the ocean. It is being pushed up, expanding. When it expands, it cools adiabatically. But then as it goes down the other side of the mountain range, it is compressing and being adiabatically heated. Therefore, it is warm when it comes in, it is cold when it hits the top of the mountain, and it is even warmer, actually, believe it or not, when it comes down the other side of the mountain. That was it. The latent heat release, by the way, there is what's happening when those clouds condense. It's not anything going on with the adiabatic. It's, remember, as the clouds condense, they're releasing that latent heat that they had to reform those bonds. That latent heat is being used. So let's look at our mountain range. What's going on here? We have one side that is very lush and green. We have another side that is quite dry. Well, this is something called the rain shadow effect. You will see this in a lot of mountain ranges all over the planet. Whatever side the prevailing winds come from, that windward side of the mountain, this same process that we just went through is happening all the time. So they're getting a lot more precipitation on the side of the mountain that receives that incoming wind. And by the time everything is rained out along the windward side of the mountain, or perhaps over just at the crest, there's very little moisture left in that air to rain out on the other side. So it tends to be very much drier, much more arid environment. You will see a change in the vegetation. And we'll learn a lot more about this when we go into the chapter on biomes and climate, I believe it is. We see this in the Hawaiian Islands. Now, the Hawaiian Islands, they're further down. They're in the tropics, so their prevailing wind is coming in from the east. If you go to the Hawaiian Islands, you will notice if you go exploring, the eastern side of the islands is their windward side. This is where everything rains out. It's beautiful and lush and green. This is where all the tourists like to hang out and imagine they're in this tropical paradise while they're fighting for a parking spot. But if you go on the other side of the mountains there, you will be surprised at how basically desolate and arid and dry that side of the mountains is.
This is a real-life example of the rain shadow effect. These are two locations on either side of the Sierra Nevada mountain range that separates California and Nevada. On your left-hand side, this location is on the western side of the Sierra Nevada, the windward side. This is quite lush and green. The vegetation, if you look at it, has very, very tall pine trees going on. On our right-hand side, this location is on the eastern side of the Sierra Nevadas, the leeward side in Nevada. And these two locations are only about maybe 40 miles apart as the crow flies. But look at the difference. Compare our leeward side of the mountain to the windward side. The leeward side is extremely arid. There's not enough moisture coming in on that side of the mountain to support the growth of very many trees. So typically our vegetation is quite low. Mainly this is just covered with like scrub and sagebrush.
And that was the rain shadow effect in a nutshell. Next, we're going to look at 4 ways to lift air: convective uplift, orographic uplift, frontal uplift, and convergent uplift. Convective uplift is basically what happens naturally in the atmosphere. When an air parcel is warmer and less dense than the surrounding air, it wants to rise. These next 3, these are what we would call forcing mechanisms. So remember when I said that a stable air mass, if it was the same temperature as its surrounding air, it would stay right where it was, or if it was colder or denser, it would sink. It would resist rising on its own. Wouldn't happen. It would need something to give it a push to get it moving upward. That push is going to be one of these 3 things. So the first one is orographic uplift. That's basically what we just went over. Wind flowing over mountains. The wind comes in, it hits the mountain, and it is forced upward. Frontal uplift is when we have a warm mass and a cold air mass meeting, and typically what will happen was that cold air mass will kind of push the warm air mass up out of the way. And then convergent uplift, this is when we have wind coming from different directions and converging, coming together. There's 2 different directions of wind come together, they slam up into each other, and they've got nowhere to go but up. These are just images showing you what I was just talking about. We have convective uplift, where that land surface has warmed and it heats the overlying air, and it starts rising on its own. We see this a lot in Louisiana on summer afternoons. We've got a lot of moisture in the air. You'll start to see those clouds building, and we can get some rain. Next, we've got orographic uplift. We already went over this. Frontal uplift. That's the warm and cold air masses meeting together, and the warmer air is pushed out of the way by the cold air. We see this a lot in the mid-latitudes. And then our last one is convergent uplift. What you're seeing here is convergent uplift at the ITCZ, the Intertropical Convergence Zone. This is important. We're going to go into the ITCZ in a lot more detail in, I believe, the next chapter. What you need to know right now is that this is the largest area of convergence on the face of the planet. What it is it's kind of a broken belt of thunderstorms and clouds that circle the Earth right around the equator. And what happens here is that we have the trade winds from the northern hemisphere and the southern hemisphere. They come together. They're both blowing equatorward. They meet basically at the intertropical convergence zone, and when they smack into each other, they are forced up. Here's the interesting thing, though. Not only is it convergence zone, I mean, it's in the name, but because it is so hot and humid around the equator, we have convergence and convection going on. What happens is those winds smack into each other, they converge, they go up, but once they start going up, just to give that little bit of a nudge to get those winds moving up, that air moving up, but then the heat and the humidity that is at the equator anyway takes over, and we just build these huge billowing clouds. So what you need to know for this upcoming exam is that, seeing that this is happening at the equator, where we know there's the most humidity on the planet, and especially over water, this area is extremely warm and rainy. We get lots of rain, lots of humidity, and it's warm. So let me reiterate that. The ITCZ is warm and rainy. Next, we're going to look at clouds. Oh no, not this slide again. Yeah, this slide again. We're going to look at net condensation one more time because it's very important for cloud formation. We know that net condensation occurs when there's more condensation going on than evaporation because evaporation has stopped. This occurs when air has reached its saturation point, the point at which its water vapor content is equal to its water vapor capacity. And as we keep seeing, when this slide keeps rearing its damp head, clouds form in environments of net condensation. So, clouds and their formation. Well, we already know that clouds are composed of suspended microscopic liquid cloud droplets and ice crystals. But did you know that all clouds take one of three forms: cirriform, stratiform, or cumuliform? And before we get into what each of those means, let me point out that we classify cloud names, on a couple of different things. The first is the form. What shape is that cloud in? The next most important is, where does it occur in the atmosphere, like at low levels, at mid levels, or high up in the atmosphere? And then the third thing is it going to produce rain or not? So let's take a look at each one of these things.
Looking at our clouds, first based on shape, their appearance, how are they formed? When we talk about clouds this way, we are using Latin roots to describe their names. So cirrus clouds, these are very high clouds up high in the atmosphere. They have a very feathery, wispy appearance. This is because they are so high up that it's super cold up there. They are composed of nothing but ice crystals. Cirrus comes from the Latin word cirro, which means curl, like a wisp of hair, hence their wispy, feathery appearance. Cumuliform clouds are dome-shaped clouds. These come from the Latin word cumulo, which translates to dome-shaped. These are those big, fat, poofy clouds that look like, I don't know, piles of mashed potatoes or piled up marshmallows, cotton balls. These are bunched clouds. They have a very flat base. Like, they are all the same base level when you look at them. And they have a billowy appearance. And then our stratus clouds, stratiform clouds. Stratus comes from the word to cover. These are kind of blankety, flat sheets of clouds. A few images here to help you visualize. First we have cirrus, our cirriform clouds. These are those high, thin, wispy clouds that form in the upper atmosphere. They have their wispy appearance because they are composed entirely of ice crystals. Our cumulus clouds, cumuliform clouds, these are those dome-shaped, billowy clouds. They have a very flat bottom. And these are our stratiform clouds. They are sheet-like. They will tend to cover quite a bit of the sky, and they have a blanketing appearance.
And that brings us to rain cloud classification. If a cloud is going to rain, we add the word nimbo or nimbus to its name. I can't think of any mnemonic for you to remember that other than if it's raining, you just add nimbo. So we have two different kinds of rain-producing clouds, and when we tack that on to the name, we're going to add it to the form of the cloud. So we have nimbostratus clouds. These are stratus clouds. They're very low level. They're in sheets, and they do produce rain because they've got the word nimbo in the name. But it's usually very light rain and prolonged. It goes for a long time, but it's basically just drizzle. The other one is cumulonimbus. These are when you start to get real big storm clouds going on. These are our poofy clouds with rain in them, hence the nimbus at the end, cumulonimbus. These guys, cumulus clouds are one where you can't really pin a level on them because you can have regular cumulus clouds low in the atmosphere, you can have them in the middle of the atmosphere, or you can get these towering cumulonimbus that you get these massive thunderstorms from. They can go so high up into the atmosphere, and they will produce severe weather many times. You'll get really strong storms. You might have really fairly short but intense downbursts. So let's take a look
at our two common rain cloud types. On your left, you have nimbostratus. These are those low gray sheet-like rain clouds where you will probably get some light drizzle. It might carry on for quite a while. And then on the right, we have our cumulonimbus. Those are the tall, poofy clouds. These are the clouds we can get thunderstorms from. The rain that comes out of these tends to be much more intense, although it may be shorter lived. This is just a quick rundown of those different cloud forms that you can refer back to remind yourself of the cirriform, cumuliform, stratiform, and nimboform.
This is a figure from your textbook showing you a few examples of those clouds. Cirrus, which is sort of thin and wispy. Stratus over on your right, which are those low clouds, low gray clouds. Cumulus down in the lower right. This is a cumulonimbus here. This is one of those big towering rain clouds. And then in the center we have something that says alto. Well, this is getting into our other way of classifying clouds, which is by level. So let's look at how that works. When we classify clouds by level, we tack on whatever level they are at with their form name. It gets kind of confusing. As you can see, there are lots of different kinds of clouds here. This is how it works. When you have high clouds, you add the word cirro in their name. At middle levels, we add the word alto, like altocumulus or altostratus. At the lowest level, we use the word strato, and we tack that onto the name, like stratocumulus. This gets really confusing. So I don't want to spend too much time on worrying about this portion of it. One thing I would like to direct your attention to here, we have a lot of different clouds going on. We've got our stratus down low. We've got our poofy little cumulus. We have our cirrus way up high. And then we have our towering cumulonimbus. That just pretty much goes wherever it wants. We will visit this guy a whole bunch more when we get into the chapter on severe weather. Meanwhile, though, look at this cloud up at the top called a cirrostratus cloud. This is a special kind of cloud. See the halo. A cirrostratus will cause a halo around the sun, and the reason why is it's up that high. It is a type of cirrus cloud. It's nothing but ice crystals. And if the sun hits it just right, it will really illuminate those ice crystals and form this halo.
And here is a picture of the lovely cirrostratus halo taken from real life.
Looking at that chart, you can tell that there are lots of different kinds of clouds. There are so many clouds we didn't even go into that are so cool, and I wish we had time to go over them, but we do not. Those naming conventions can get pretty gnarly though, so we're not going to focus on any fancy names. What I would like you to know for the exam, know this, it is important. I want you to be able to describe the basic characteristics of those 3 cloud types by shape: cirrus, cumulus, and stratus. Then I want you to be able to identify what's special about a cirrostratus cloud. Know that if a cloud has nimbo or nimbus in its name, it means that is a rain cloud. And then what words are added to cloud names when describing by level? Remember, if the cloud is at a high level, we're going to tack on the word cirro or cirrus in there somewhere. If it occurs at the middle level of the atmosphere, we are going to add the word alto. And if it occurs low in the atmosphere, we're going to add the word strato or stratus. So those are the basic cloud types. But there's one more basic cloud type that we haven't mentioned yet, and you might not normally think of it as a cloud. What is it? Fog. Fog is basically just a cloud that forms close to the ground, reducing the visibility. If you'd like a little more professional sounding explanation, it is a dense collection of water droplets suspended in the air close to the Earth's surface. Because it obscures visibility, this can be really problematic for driving. If you've ever tried to drive in a thick fog, I'm sure you understand this. It also makes navigating boats, ships difficult, and it's a real problem in aviation when those pilots are trying to land those airplanes in a fog. Have you ever been on an airplane and the pilot comes on and he says, folks, they've got a thick fog over, insert the name of your airport here. We're going to make a few circles and come in a little bit when the fog is lifted a little bit. And they tell you you'll be down in like 5 minutes, and then 30 to 40 minutes later, you finally get down to the tarmac. Fog really increases the risk of traffic accidents, all kinds of accidents where we're involving a moving vehicle of some sort, and delays. There are several different kinds of fog that form under various environmental conditions, but all of them form where air at the Earth's surface is cooled to the dew point. This is what all types of fog have in common. You have to get that air right down near the Earth's surface cooled to saturation. Now, if you are somebody who is really turned on by fog and you would like to learn about the many varieties of fog that are out there, do consult your textbook. But right here, right now, we are only going to focus on 2 of the more common types: radiation fog and advection fog. So radiation fog forms typically on cold, clear nights with very little wind. And what happens is, as the Earth's surface cools off throughout the night, It's emitting that long-wave radiation back out to space. It is losing heat rapidly on very calm nights where there's little to no wind and there's no clouds to help keep that long-wave radiation in. That land surface will cool extremely quickly. If there is air above that land surface with any kind of moisture in it, any kind of humidity, that warmer air coming in contact with the cold Earth's surface is going to immediately condense into actual liquid droplets. The vapor in the air will condense to liquid droplets and form that fog. This is an example of radiation fog in California's Central Valley. This wide swath of white in the center is actually a bowl-shaped valley, and the white is a radiation. It's actually a special kind of radiation fog called Thule fog. But it is radiation fog that has formed because it was a clear night the night before, and the Earth's surface got super cold, and there's a lot of ag in the Central Valley, a lot of agriculture, so there's quite a bit of moisture, and it forms this radiation fog. Big note here. Radiation fog does not form over water. It only forms over land. You know what does form over water?
Advection fog. Advection fog forms over water. We have two instances here of that advection fog. On the top, we have a little tugboat that is currently in this photo sailing through Lake Pontchartrain. That is New Orleans in the background. Our bottom photo was taken in San Francisco. That is either the Golden Gate Bridge or the Bay Bridge. It's one of their bridges. And you see that the bridge is surrounded in fog. Well, beneath that fog is the San Francisco Bay. So advection fog forms when warm, moist air moves over a much colder surface, almost invariably a water surface. So we are talking rivers when they're very cold, like the Mississippi River when it's cold, lakes, oceans. This is a big one for oceans. Pretty much any kind of fog that's going to form over the ocean is going to be advection fog, especially over cold currents in the ocean, such as the cold California current that runs along the western coast of North America. Also, it can even form when warm, moist air, or at least relatively warm, moist air, passes over glaciers. So what goes on in this instance? Remember that our heat is transferred from warm to cold. Well, what's going on here is as that warm, moist air passes over the relatively colder surface of the water, it is giving up some of its heat to the water, and this causes its vapor pressure to go up, and that causes it to condense. So that is it for advection fog. I would like you to check out, if you get a chance, this video that I have linked down at the bottom. It's called Adrift. It was an award-winning video. It is fabulous. It's a picture or a video of advection fog forming in the San Francisco Bay and then creeping over the hills. It's very cool. You should check it out. I have it up on Moodle in the helpful videos section. So we have covered the basic cloud types, the most common cloud types that will be on your exam. And I know I said that we did not have time to look at any other clouds. I lied. You know why? Because clouds are cool. There are so many different exotic, amazing kinds of clouds that can go on that we just don't have time to cover. But let's take a quick look at some of them. What are some of these clouds? Well, let's see. How about Kelvin-Helmholtz clouds, Mammatus clouds, roll clouds, pyrocumulus clouds, Arcus clouds, wall clouds, shelf clouds, spiral clouds, rotor clouds, lenticular clouds, wave clouds, and last but not least, the lovely Angulus asperatus cloud. These are just a few of these amazing cloud forms that can develop in our atmosphere under a whole bunch of different conditions. So I encourage you to keep looking up. So that was it for our quick look at the different cloud types. Now we're going to move on to how clouds affect the larger climate.
Clouds can affect the larger scale climate through what we call cloud forcings. And it's kind of a two-way street here. Temperature can change the amount of cloudiness, but cloudiness can also change the temperature. So clouds will cool the Earth's surface and atmosphere through something we call the high albedo cloud forcing effect. This is what happens when cloud surfaces the tops of the clouds rather, when I say surfaces, I mean the tops of the clouds, reflect that incoming shortwave radiation back out to space. That has a cooling effect. That is the cloud albedo forcing. This is a negative forcing, and we'll get into what that means in just a second. Right now, here's a figure from your textbook. On top, we have clouds interacting with incoming solar radiation. The incoming solar radiation hits the top of the clouds. Some of that is absorbed by the clouds and radiated back down to Earth, but a lot of it is bounced off. It's reflected back into space because the clouds have a high albedo. They're very reflective. And then beneath that, we have a map showing global albedo distribution of the Earth for the month of June. The white areas are areas of high albedo. Notice that coincides with the ITCZ around the equator, where we have a lot of cloud cover. And then the mid-latitudes, where we also get just a lot of weather, a lot of storms forming. Those dark sections on either side of Africa, the top one is the Sahara Desert. There aren't any clouds there. There's nothing reflecting that back. So it's really low albedo, and a lot of that solar energy is being absorbed there. We've got some deserts down in southern Africa too, so that's what's going on there. That was cloud cooling. Clouds can also warm the atmosphere, and they do this by absorbing that long wave energy that's coming from Earth's surface. As that long wave energy is going up from the surface towards space, it's intercepted by the clouds, and the clouds are, because they're water vapor, remember, they're really good at absorbing heat. They absorb that heat along with the other greenhouse gases in the atmosphere, and then they re-radiate it back down to Earth, adding to the warmth. We call this the cloud greenhouse forcing. This is warming process, and it is a positive forcing. What we're looking at here is a satellite image of outgoing long-wave radiation, the radiation that's being emitted by the Earth back out to space. Notice the big swath across the tropical regions. That's where all those clouds are. They are intercepting some of that long-wave radiation and absorbing that heat. Notice there's much less going on as you get further towards the poles. Well, there's just less heat to be emitted by the Earth. So we've been saying positive and negative forcings. What we're really talking about here is feedbacks. Remember, feedbacks, these are changes in a system that cause other changes, kind of in a cause and effect chain of reactions. Within that system, it either causes a positive or a negative feedback. With a negative feedback, the process is something's going on with the interacting parts of that system that act to stabilize the system. Something's going to change, but then whatever changes is going to kind of regulate itself back down to the original state of the system. With positive feedbacks, this is where those interacting parts, what's going on, destabilizes the system, and the system does not go back to its original condition. It has to go to a new condition. When we're looking at that in terms of cloud feedbacks and how they affect temperature and climate, cloud negative feedbacks will keep the temperature stable. An example of that would be the reflection of solar energy back to space. So if we have some stratus clouds, some of those low sheet-like clouds, they're going to reflect a lot of incoming solar energy back to space. It's a negative feedback because it's going to cool the Earth and reflect that incoming solar radiation away from the Earth. It's going to be a cooling, negative feedback. Cloud positive feedbacks will change the temperature. Example here, we have cirrus clouds. Those are those high, thin, wispy clouds way up high in the atmosphere. Cirrus clouds really like to absorb that long wave radiation that the Earth is sending back out to space. When it absorbs the long wave radiation and it tries to readmit it, it is warming the atmosphere. This leads to a warmer atmosphere. Well, a warmer atmosphere is going to lead to more evaporation of moisture at the land's surface. More evaporation means more moisture in the air. It means more cirrus clouds. Then they start the cycle over again, and it just keeps feeding on itself. That's a positive feedback. Note these examples. Note that I have example in red. That's because these might be on the exam. And then finally, so if we look at like comparing our negative and positive cloud feedbacks, is it sending most of that energy out to space? Is it reflecting it, or is it sending it back down to Earth and warming the Earth? If you add up both of those and you take them as a whole, cloud feedbacks are causing net cooling worldwide. They're actually keeping the Earth a little more cool than they are warming it. And that is the end of this part of the lecture.
So now we're going to switch over to looking at precipitation. What happens after those clouds form? We know that as water vapor moves up in the atmosphere and is cooled, it is going to condense into water droplets, which form clouds. But here's the thing. Water likes to stick to itself. We know that. That's called cohesion. The water wants to join itself, but it can't condense to itself. Enough of those droplets condense to form a real water droplet that's going to make up clouds. The water vapor needs some kind of surface to adhere to start growing those water droplets. So what these surfaces are is we have things in the air that we call cloud condensation nuclei, which is just a fancy word for microscopic little small particles of things we have already talked about when we talk about aerosols: dust, bacteria, salt, smoke, pollen. You get it. These are extremely small particles in this instance, and once we have some water droplets condensing onto them, or water vapor condensing onto them and causing water droplets, they become what we call cloud condensation nuclei. So this is the base for all precipitation forming from this point. Our water vapor in the atmosphere needs a surface to condense onto. We call that surface, these microscopic particles, cloud condensation nuclei. Precipitation forms through two main processes, something called the collision coalescence process that occurs in the lower and middle sections of the cloud, and then something called the ice crystal process that occurs in the middle and high sections of the cloud. The first of those processes, the collision and coalescence process, this occurs in the lower to middle sections of the cloud. This is how we get rain. If you have liquid precipitation, rain, it has formed through this process, the process of collision and coalescence. How this works is we have your water vapor condensing around a cloud condensation nuclei. You now have a water droplet. Inside the cloud, air is still moving. So all these little water droplets are floating throughout the cloud. They're being moved by updrafts and downdrafts, and they're smacking into each other. As they smack into each other, as they collide, there's the collision portion, they're going to join together. They are going to combine. They're going to coalesce. So as these rain droplets, as these water droplets are smacking into each other and coalescing, they are forming larger water droplets. And this process is going to continue until that water droplet is large enough and heavy enough that gravity takes over and it falls to the ground as rain. With snow, we use the ice crystal process. Snow is formed through something called the Bergeron-Findeisen ice crystal process, and this occurs in the middle to high levels of the clouds. Here what's going on is we are having water vapor condense onto cloud condensation nuclei, but in this case it preferentially wants to form around flatter nuclei, plate-like shaped nuclei, and we can just call those ice nuclei. Inside the cloud, we have these little ice crystals forming, but there's also something called supercooled water droplets up in these high areas of the clouds. Supercooled water is water that is below the freezing temperature, but it's still in liquid form. It's a very interesting thing. We're not going to get into it here, but if you would like to learn more about supercooled water, take a meteorology course. We do offer those. So what's going on with the ice crystal process is that we get our initial little ice crystal that has formed. It continues to grow by preferentially like pulling that water vapor away out of the supercooled water droplet, and then it evaporates from that supercooled droplet and deposits, freezes onto the ice crystal. And this is how those ice crystals begin initially. Air is still moving in the cloud, so the ice crystals are then also going to bang into each other, and some of them are going to shatter. And in this instance, they're not actually combining. What's happening is those new smaller pieces of ice will start the process over again, and they will start to draw vapor away from the supercooled water droplets. It's going to form on that, adhere to that ice crystal. It's going to freeze onto that, and it's going to cause that ice crystal to grow. This is why all of our snowflakes are different shapes. Supposedly, you will never, ever find two snowflakes that are the same shape. It's quite possible. I don't know. I'm not going to live long enough to find out. But this is because these crystals are forming all over the place as they shatter and absorb more of that supercooled water, having it freeze onto them. So they are getting all kinds of different things going on, and you get different shapes. This is just a figure from your textbook, walking you through that ice crystal process. We're not going to dwell on it here. You can go look at your textbook. Let's move on and learn about warm and cold clouds. Warm clouds are liquid clouds. Warm clouds are those in which the precipitation is forming in temperatures above 0 degrees Celsius, so warmer than the freezing point. There's only liquid water in the cloud, and only the collision coalescence process is occurring. That's the only thing that's going on. Therefore, warm clouds make only rain. Cold clouds are your ice crystal clouds. This is where precipitation is forming at or below 0 degrees Celsius. In the cold clouds, the ice crystal process dominates. Cold clouds can still make rain, but primarily they make frozen precipitation, that's snow, sleet, and freezing rain. Why I say they can do both is because within the cold cloud, there is a section between 0 degrees Celsius and negative 15 degrees Celsius where both processes are occurring. You can get frozen precipitation and rain. We call this portion of the cloud the mixed phase. So where you've got both types of, both the ice crystal process and the collision and coalescence process going on, is that slightly warmer section of cold clouds, the mixed phase section. So here we have a cross section of the atmosphere. Notice the temperatures that are marked here, 0 degrees Celsius and negative 15 degrees Celsius. From 0 degrees Celsius and up warmer, we get that collision coalescence process. We have warm clouds. This region is going to produce rain. Then if we go from negative 15 degrees Celsius and colder, we're looking at clouds that are forming precipitation using the ice crystal process. And those are going to give us our frozen precipitation, snow, sleet, freezing rain, etc. In between these two temperatures, between 0 degrees Celsius and negative 15 degrees Celsius, we're going to get both things going on. Both processes are happening. Right here, we have both liquid precipitation and ice crystal precipitation going on within this region. And so this is going to be our mixed phase region. This figure from your book is showing you the temperature profile that we will see under different types of precipitation formation. I'm not going to go through these. You can read this in your book. A very quick look at some of the ways we can measure precipitation. Starting left and working our way right, we have a rain gauge, which we measure liquid precipitation with rain. Right next to it, we have something similar called a snow bucket that we use for measuring snow. Measuring snow with a snow bucket can be a little problematic because sometimes you will have snow blowing into that bucket sideways, so it's hard to tell exactly if what we're measuring is what really came down in that one limited area, or if it kind of migrated in from somewhere else. Another way that we can measure snow is with a snow stick. The person goes out, they shove this snow stick down until it touches ground, and they measure the depth of the snow. And then our right, we have a Doppler radar image. We use Doppler radar for looking at precipitation a lot of times because it kind of can peer through those clouds and that precipitation and see what's going on there. Remember, I said that hail didn't form quite the way that some of our other precipitation did. It's not necessarily from that collision and coalescence process or the ice crystal process. First, a quick definition. Hail is hard, round pellets of ice of either 5 millimeters in diameter or greater. And hail forms exclusively in cumulonimbus clouds. These are our tall, billowy clouds that we get thunderstorms from. So how it works with hail is these ice pellets will form in very high up in the cloud, in that cold cloud section. With thunderstorms, they kind of have a unique setup of how they work, and we will find out more about that in that severe weather section. But what happens is towards the one half of the cloud is getting an updraft of warm air from the surface, and another half of the cloud is pushing down. It's all that precipitation is coming down to the surface. So we have warm updrafts going up, colder downdrafts coming down. What happens with hail is we get these little round pellets of ice called graupel in that upper level. The graupel collects until it gets really heavy, and then gravity kicks in and it starts to fall down through that cold portion of the cloud, through that mixed phase portion of the cloud, where it's between 0 degrees Celsius and negative 15. As it starts to descend towards the ground, it runs into those warmer air coming up and it starts to melt. But that air coming in from the bottom pushes it back up into the cold section, and then this allows more ice to freeze onto it, making it increase in size. And it will keep doing this series of sinking down, hitting the updrafts, going up, icing down, or icing, coming back down, melting, going back up, collecting ice. And it keeps doing this and adding layers as it goes until it gets so heavy that gravity just can't hold it up. And then it comes down in that downdraft side of the storm as a hail shower. Hail can cause a lot of problems. It can destroy crops. Farmers hate hail. It can make a terrible mess, just destroy an entire field full of whatever is growing, especially if that crop is fairly delicate. Off here we have a picture of a cornfield. Corn's not that delicate, but they had a really severe hailstorm here and just wrecked the whole crop. Hail can destroy property, like this poor vehicle here. Hail can damage roofs. It can harm livestock. It can be a real problem. And of course, the larger it is, the more damage it can cause. So how large can hail actually get? Well, it can get this big. This is a hailstone that happened, I believe, in Vivian, South Dakota. As far as I know, this is still the world record holder for the largest hailstone ever recorded. It was almost 9 inches in diameter and weighed almost 2 pounds. So it is between the size of about like a softball and like a small child's bowling ball. If something like this hit your car, you best believe you will be filing an insurance claim. These people are experiencing the joys of being caught in a hailstorm firsthand. That is it for this lecture. In fact, this is it for Chapter 4. Our next video is going to start on Chapter 5, Atmospheric Circulation and Wind Systems.